um, over the quest. Um, I've gone through all of the responses, added back some partial credit where it was warranted, and I just wanted to go over a few of the high and the low points, right? Um, the average was a 78 and a half, which is not terrible. First time around, we weren't exactly sure what to expect. Um, it's that C plus, B minus range. That's sort of where I expect the average to end up at the end of the semester. And so, I think this is probably about an average quest. There were a few of you who didn't do great. And I want to bring up this oopsie daisy. Maybe you saw that in Moodle. An oopsie daisy is a way for me to recognize that not everyone is always on their A game, right? Maybe you've had an off day and you bombed a quest or you slept through lab or whatever. An oopsie daisy is just a way for you to get that opportunity back. And so everybody has one redo that they can do throughout the semester. The rules for an oopsie daisy are that you have to let me know that you want to redo that particular assignment. So it can be retaking a quest, it can be redoing a lab, or it can be getting an extension on an ALEKS assignment. So any of those, you just have to let me know within 24 hours that you want to use your oopsie daisy. And then you have to actually do the makeup work within a week. Right? That being said, I just want to also remind you that this course is 500 points total. And so if you missed 5 points on the first quest, that took you down from 100% in the class to a 99% in the class, right? It's not, even though it shows up as a 66.7% in the gradebook for that one assignment, overall, that's just 1% out of your total grade. And so I'm not trying to deter you from using it, but if you want to use it, just make sure that you have thought through and that you're sure you want to use it this time around. Okay. Some things from the quest. Don't forget sig figs. There were a couple of people who it gave you a number to write in scientific notation, and you rounded that number. You dropped significant figures. I don't know why. And so just keep an eye out for sig figs. When you write in scientific notation in Moodle, right, the E character takes place of the times 10 to the, and so you don't need the caret, you don't need the 10 or the multiply or anything like that. And so the E is the times 10 to the part. And so you just need the number and then the exponent. In the calculator, several of you, the one where it had you divide two numbers that were in scientific notation, it was obvious from your answer that several of you forgot to put parentheses around that number, or you forgot, or you didn't use the exponent button. If you're having issues with that, we can do a private Zoom or something. But that's the most efficient way to use your calculator, and I encourage I encourage you to get familiar with that method. The last thing is that going forward from here on out, we're into naming compounds now. You need to be able to go back and forth between the symbol and the name for the first 92 elements. Right? The periodic table that ALEKS provides and the periodic table that you'll get in Quest will not have the names of the elements on there. It'll just have the symbols, the atomic mass, the atomic number, that kind of thing. And so you're going to need to be able to go back and forth between a symbol and a name for quests from now on. Also, that table of polyatomic ions, it's in this set of slides for chapter 2. It's also in the video that's on YouTube from the lecture on Monday. That set of polyatomic ions you'll need to know for naming purposes, right? You won't get that on a quest. and so you need to know, I think we said it was 24 ions that you'll need to know for quests from now on. All right, any questions about quest 1 that we should go over? Any questions about Noopsie Daisy?
Where can we find our test grades?
So if you go into Moodle, you can click on grades. The quest grade is there. And this afternoon, Ryan has gotten me your lab grades. And so this afternoon, I'll put lab grades in from both last week and this week. And so that's as up to date as our grades will get. Right? Okay. All right, hearing no questions, seeing no hands, let's move on to continue with naming. So we left off talking a little bit about transition metal ionic compounds, and we used our Roman numerals to sort of describe what the charge was on those ions, since they can take on multiple charges. And so I just wanted us to do a little bit of practice with some compounds going back and forth. These are not all transition metal compounds, but these are all ionic compounds. All right, so I'm just going to give you a minute here to sort of work through these on your own, and then we'll come together to go over them. In the meantime, I'm going to get a drink of water for this frog in my throat.
Dr.
All
Davis.
right. So for this first one, what did we come up with?
Copper 2 nitrate.
That's right. We recognize that copper is a transition metal. So we're going to put in, we know we need a Roman numeral. We know that it's a 2 because we know the charge on nitrate's -1. There's 2 of those. So we must need 2 positive charges to balance it out, copper 2 nitrate.
Dr. Davis.
Yes.
Are you going to post the recording from the last lecture that we had? I think it was Monday.
I am. It is. I did it just before this class, actually.
Oh, okay, perfect. Thank you.
It should be up there now.
Yes, sir. Thanks.
Yeah. Okay. This second one requires a bit of trickery in its naming. Who came up with a name for B?
Is it potassium dihydrogen phosphate?
Yeah. So there are a couple ways of naming this, but potassium potassium dihydrogen phosphate is a great way. Okay. We think about this dihydrogen phosphate as a single polyatomic ion sometimes. I know that this one's not on your list, And so you do not need to sort of memorize this or anything. But we can also think about this as separate pieces, right? Because that's how we name it. We have our phosphates and we have our hydrogen, 2 hydrogens, and we have our potassium. And so we can kind of think about it either way. And it turns out that naming convention is the same for both of those. All right. This last one, we start with a polyatomic ion, and we end with a polyatomic ion. What do we have?
Ammonium chlorate.
Ammonium chlorate. That's right. Remember that ammonium is NH4 plus. NH3 is a compound that we will talk about a good bit in this course, and that is ammonia, not ammonium. And just be sure that you don't get those two confused. So ammonium has the extra hydrogen with an extra plus charge, and ammonia is just NH3. Okay? Ammonium chlorate. All right, one more. Going from a name back to a formula. I have somehow managed to change all of my controls on my writing tablet. I need to figure out how to get it back to normal. All right. Mercury 1 nitrite. What's our atomic symbol for mercury?
HG.
Hg. Yeah. And it tells us it's a 1 plus charge. What is nitrate?
NO2.
NO2 with a negative charge. Yeah. This is another tricky one that the book gives us. It turns out that mercury 1 is not very stable by itself. It just is one of those elements that really doesn't like to be by itself when it has this +1 charge. And so what ends up happening is that mercury 1 is actually 2 mercury atoms that hang out together, and they have a 2 plus charge. And so each mercury has a 1 plus charge. But this Hg2 2 plus is really what we're working with. And so it's Hg2 NO2 2, right? I don't deal with mercury a whole lot, but I have seen some places where they go ahead and reduce this down to HgNO2. I've seen some places that leave it as Hg2NO2 2. Because of that, you'll notice that mercury 1, is not on our list of polyatomics you need to know, right? I'm not going to worry about it because we can't seem to come to agreement on what it should look like. but I wanted you to see it just in case Alex brings it up. I don't have complete control of the questions on Alex, and so I just wanted you to see it just in case it pops up in the homework.
Is it the same for oxygen? Because when I was on Alex, it did that to me with oxygen.
So oxygen is one of those 7 elements that it always exists by itself as a diatomic molecule. We talked about the fact that there are 7 of those: nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. That's 6, but they form that corner of the periodic table that kind of looks like the number 7 to remind you that hydrogen is the 7th one, right? And so there are 7 elements. When they're by themselves, not bonded to any other elements, they are always going to be diatomic. Griffin, when we look at an atom of oxygen by itself, it's been split from O2. And usually when we have ions of oxygen, they're going to be just a single oxygen atom that has gained some electrons. It's not usually going to be O2 with a negative charge as the molecule.
Okay, thank you.
Yeah. Cesium sulfide, what do we come up with?
Is it C2S?
So cesium is not just C.
CS2S.
CS2S, absolutely. So the IDE ending is indicative of it just being the element rather than a polyatomic ion, right? And so we know that we need some sulfur. Sulfur is in the same group as oxygen, which tells us that it needs 2 electrons added to it to get to that noble gas status. So it's a 2-, cesium is a 1+, and we end up with cesium-2 sulfur. And calcium phosphate, the last one. We have calcium. What's the charge on calcium?
2.
2+, it's in group 2, those alkali earth metals. And phosphate is?
2-.
It's not 2-. What's the formula for phosphate?
PO4, 3-.
PO4 with a 3-. That's right, Cameron. And so we do our little switcheroo thing. We end up with calcium 3. And since we need more than 1 phosphate, we're going to put it in parentheses, and we need 2 of those. Any questions or concerns going from name to formula here? All right. Hearing none, that sort of wraps up ionic compounds. We didn't quite get that covered on Monday, but that's the end of ionic compounds. And now we're switching gears to molecular compounds. We talked about how ionic compounds are held together because they're positive negative ions. We call that electrostatic forces. Molecular compounds are held together because they share electrons. And so these are covalent bonds. Which is sharing of electrons. Okay. The naming here is really straightforward. We're going to take the first element, and if there's more than one of them, we're going to add a prefix, but we don't really change the name other than that. For the second element, if there's more than one of them, we're going to give it a prefix, and then we're going to change the ending to IDE, just like we do for ionic compounds, right? So generally speaking, these are nonmetals that bond with other nonmetals And sometimes those metalloids, right? Remember those things that can't really make up their mind if they're metals or nonmetals. And so sometimes a covalent compound, a molecular compound, can be between nonmetals and metalloids. Many of them have common names, right? So if we look at H2O, right? You and I and everybody knows that that's water. But if we were to name this according to the system, right? Well, there's 2 hydrogens, so we're going to use that prefix di, dihydrogen. Okay. There's 1 oxygen, so we're going to pick up a mono, and we're going to change the ending to IDE. So we have monoxide. Okay. We also remove repeated vowels, so monooxide. We just drop one of those O's, so we get monoxide. Right. Dihydrogen monoxide. Ammonia is another good example, the one I just talked about. Right. We're going to call it ammonia most of the time. But if we wanted to write it out, then it would be nitrogen trihydride. Right. Let me point out here, for the first element, we don't use mono if there's just 1 atom. Right? We just, it sounds funny, and we know that there's 1 because there's no mono, pretty much is the way it works. Okay. So let's do some practice here. Take a minute and work on these. And then I'll see where we end up. All right, I'm just going to go across the row that's on my screen here. May, do you have the first one?
Oh, do you call me?
May?
I'm a little bit confused on how to do this.
Okay. So do we know the name of that element?
Oh no, I don't know how to get unmuted.
SI?
Silicone?
Yeah. And then what's our prefix for 4?
Tetra?
Tetra. And what's our second element?
Chlorine?
Chlorine. Do we leave it as chlorine?
Chloride?
Chloride. Silicon tetrachloride. Absolutely. Again, we don't need the mono for that first one. We dropped the mono from the first element, so we don't need that. Okay. All right. Okay. Vanya, how about the second one?
Tetraphosphate decaoxide.
So you're almost there. The element here is not phosphate. What is it?
Oh, phosphorus.
Phosphorus. Yeah. Tetraphosphorus, and then we have decaoxide. Again, I told you we could repeat. We could drop a repeating vowel. We could make this decoxide. Again, that's one of those things that I've kind of seen both ways. It really doesn't matter to me if you write deca or decoxide. But yeah, absolutely. Tetraphosphorus, decaoxide. Yeah, and good to point out that phosphorus and phosphate are different things. So we need to just pay careful attention to that. Alexis, how about the next one?
Hydrogen monoiodide.
That's it. Hydrogen monoiodide. Abigail, do you have D?
Yeah, is it hydrogen trifluoride?
Not
I mean
hydrogen.
nitrogen. Sorry, nitrogen.
Nitrogen trifluoride. Absolutely. And this last one, Michael, you got it?
Is it dinitrogen oxide? Oh, monoxide?
Dinitrogen monoxide. Absolutely. Okay. And so naming these is relatively straightforward, right? As long as we know those 10 prefixes, we should be pretty good. And of course, again, this is why we need to know what those element names are as well. All right. Going the opposite direction, let's see if we can do these a little bit faster. Cameron, how about this first one? Carbon disulfide.
CS2.
CS2, easy enough. Griffin, do you have B?
Sorry, you couldn't hear me. Yeah, Si2, BR6.
BR6, absolutely. Si2, BR6. All right, Nathan, do you have sulfur dioxide?
SO2.
SO2. Ashlyn, dinitrogen tetrachloride.
N2 Cl4.
You bet. And Taylor, dihydrogen monoxide. We've already done this one actually. H2O. All right, so going back and forth.
Sorry, not just but H2O.
Yeah, absolutely. So going back and forth from name to formula for molecular compounds is, in my opinion, a bit easier than for ionic compounds. There's not quite as many rules to remember. It's just knowing those prefixes. Okay. So moving on to acids. Acids are a special category of compounds because they break apart in water, right? If you look at our image over here, we have HCl, which is our acid. And when we put it in water, we get that Cl minus by itself. And then we get H3O plus. Really, what happens is HCl reacts with water. And we get the Cl minus by itself. But the H plus joins up with water. So we get H3O plus. We'll get more into balancing equations and things like this in chapter 4, tail end of chapter 3. This ion is hydronium. Right? It's a polyatomic. You don't really have to know it because it doesn't react very well. It doesn't form ionic compounds very well. It's way too reactive, actually, and so it won't stay as H3O+. It would much rather just give up that H+ and go back to being water. Right? But there's a special set of rules for naming. When we have it by itself, so as a pure substance, we follow the standard molecular rules for naming molecular compounds. Right? And so HCl, following those rules, what would it be?
Hydrogen chloride.
That's right, hydrogen. I'm going to say monochloride. Right? But as soon as we put it in water, that's when that acidic nature starts to come out. And so if it's dissolved in water, then we're going to use acid naming rules, which we'll talk about in a bit. And HCl becomes, anybody know? Am I familiar with this?
Hydrochloric acid.
Absolutely. Hydrochloric acid. Oh, missed my dro. Hydrochloric acid. Okay. And so we do have some rules for naming. Okay. Oops. I need to add an extra slide in here. Let's see here. All right, so this is acid naming. So the naming of an acid depends on the ending of the anion that was used to make that acid. So the anion ending if it ends with IDE, like the one we just did was hydrogen monochloride, right? That ends in IDE. The acid name becomes hydro, whatever the anion is, ic acid. Right? So we had hydrochloric for Cl minus. Right? If it ends in ITE, then it's going to end with OUS when we name it as an acid. And so this was HCl. An example is hydrogen nitrite, right? Nitrite, HNO2 becomes nitrous acid. Okay. And if it ends in ATE, it's just going to be ic. Okay. So sulfate, H2SO4, sulfate becomes sulfuric acid. This one is a bit of an odd one to the rules. That's why I put it down as an example. It doesn't become sulfate, doesn't become sulfic. It becomes sulfuric. I guess somebody thought sulfic sounded weird. So sulfuric acid. Let me give you one more here. If we have HClO4, this is, well, let me do ClO3. This is chlorate, right? And so this becomes chloric acid. And so those are our acid naming rules. The reason that it depends on the anion name is because the cation is the same for all acids, right? What's the cation for all acids?
Chlorine?
Hmm?
Oh, is it hydrogen?
Hydrogen, absolutely. H plus is our cation for all acids, right? And so to name it, we need to differentiate based on what the anion is, right? All right, so if there are acids, there must also be bases. Acids and bases, of course, are sort of opposite one another, right? We'll talk more about acids and bases in chapter 4. But just like an acid generates that H3O plus in water, bases generates OH minus in water. And so what do we call the OH minus polyatomic ion?
Hydroxide.
Hydroxide, absolutely. Okay, and so our bases are going to be ionic compounds that have hydroxide in them, like NaOH, KOH, BaOH2, right? And there's really nothing special about these names. I just want you to recognize that things that have hydroxides usually are bases, right? And so this would be sodium hydroxide, potassium for K, and what element is Ba?
Barium.
Barium. Right. Now I don't need Roman numeral parentheses for any of these because none of these are transition metals, but if I did have a transition metal hydroxide, I'd have to throw in those Roman numerals. Okay. All right. A couple of unique cases, a couple of things to talk about that are kind of non-standard. The first are hydrates. And so occasionally, some crystals, some ionic compounds when they form crystals, they trap water in that crystal structure. We want to be able to note this when in the name and in the formula, because if we're going to measure out and we want to get a mole of copper sulfate, for example, well, copper sulfate rarely comes without water. It usually comes with a few waters hanging around. And so if we're going to weigh it out, we have to account for the mass of that extra water that's part of that crystal. And so, for example, copper sulfate, copper 2 sulfate, comes with 5 waters. And so this little dot here represents that they come together. That water is a part of that crystal. Okay. And we name it, well, the first part is easy. That's the part that we have talked about already. Copper. Copper's a transition metal, so he needs his Roman numerals. Again, we know that his Roman numerals are 2 because sulfate has a 2- charge, and that copper has to balance it out. To talk about the number of waters, we have to use those prefixes. What's our prefix for 5?
Penta.
Penta. And so we just say pentahydrate. Right? If any of you have used Epsom salts are magnesium sulfate heptahydrate. What would be the formula, the full formula for magnesium sulfate heptahydrate? What's our charge on magnesium?
2+.
And on sulfate?
2-.
2
Oh, wait,
minus?
no.
Yep, that's right, that's right. So we end up with MgSO4. What's that hepta prefix?
.5.
That's
7.
penta.
Oh, dot.
Lily, did you have it?
I'm not sure.
7.
7, there we go. So dot 7 H2O. Yep. Absolutely. Okay. And then on the slides there's just a little image of what copper sulfate pentahydrate looks like relative to copper sulfate without the water, right? It's if you've ever seen it in person, it's a much prettier crystal with the water as part of it. Okay. All right. The last thing to wrap up with is talking about organic compounds. Now, you will do much, much, much more naming of organic compounds if you make it to Chem 203. But we're going to talk about just the simplest family of organic compounds, and these are alkanes, right? We call these hydrocarbons because they're only made up of 2 elements. I bet you can guess hydrogen and carbon, right? The thing to keep in mind for this, and we'll discuss this later in the semester, but carbon really likes to make 4 bonds. And so if there's just 1 carbon atom, he's going to make 4 bonds to 4 different hydrogen atoms. And so CH4 is our lowest one. If we were to sort of sketch him out, I'm not going to do this for all of the ones I want to talk about, but oof, where am I going? I'm getting ahead of myself. CH4 looks just like that. This compound is called methane. That prefix meth is sort of unique to organic naming, and so things with 1 carbon use the meth prefix. The ane comes from the fact that these are alkanes, right? If we move up to 2 carbons, C2H6, that's the maximum number of hydrogens we can get around 2 carbon atoms that are bonded together. He's ethane. C3H8's in your gas cylinder for your grill. What's that one?
Propane.
Propane. C4H8, or sorry, C4H10 is in the lighter for that grill.
Butane.
Butane. Those are the only four that have kind of funny prefixes. Once we get to 5 carbon atoms and up, C5H12, we revert back to our prefixes we know and love. This is going to be pentane, right, with the penta prefix, C6H14, hexane, etc., etc. Okay. And so these are the alkanes. The only reason I'm showing you this is because they kind of use that different prefix, those different prefixes there for the first 4 hydrocarbons, alkane hydrocarbons, right? Meth, eth, prop, and bute. I'm sure, again, there's something out there for a mnemonic to remember that. Okay. Generally speaking, to come up with this formula, it's n number of carbons and 2n plus 2 number of hydrogens. Right? And so if you wanted to figure out what octane was, goes in your gas tank, right? Octane would be C8, because we know it's 8 from the prefix, and then H18 from 2 times 8 is 16 plus 2. Okay. So that is, that wraps up naming. That also wraps up chapter 2 for us. We will move into chapter 3 on Monday, but you should have now everything you need to complete the next ALEKS objective. That's due Tuesday at midnight. That covers talking about formulas, empirical versus molecular formulas. It talks about ion symbols and counting numbers of subatomic particles. It also deals with atomic mass and figuring out isotopic mass like we did in lab yesterday. So if you have any questions about that kind of stuff, one quick thing before you go. On our Moodle page, I have added a link. Can you see our Moodle page? Yes. Good. For the Zoom office hours, I'm going to use this website called Appointlet. If you click there, you can schedule a 5-minute office hour session, 15-minute or something a bit longer if you really would like. But if you click on it and you just have a quick question, it'll show you the times I'm available for that week. And so Friday office hours, I don't plan on having any in the afternoon, but Monday it'll show all the times I'm available on Monday for chatting. And because we chose a 5-minute time block, it's every 5 minutes. So there's a lot of options there. But you can come in and you can schedule an office hour session with me if you'd like. Okay. All right. Any questions before I let you go for the weekend? All right. I hope you have a good weekend. Let me know if you have any questions or if you need anything about ALEKS Chapter 2, any of that. Okay?
Thank you.
Take care.
Thank you.
Thank you.